problem solving session 1. So the whole feel of this now changes, and this is one of the most fun sessions, I think, in the whole course. So I hope you enjoy it as much as people have done in the past. So what we're going to do is we're going to introduce you to some experiments using the seahorse, and then we're going to, having gone through some live interaction about the interpretation of those experiments, we're going to turn you over to the breakout rooms where you can discuss in your small groups, the ones you've just been in, what you think the answer to a particular question is, and then join the main session again to discuss it, and then next question back into your room, etc. So there are 3 different things to discuss. There's 2 types of experiments, electron flow and coupling, and they're used in an investigation of the sites of actions and effectors of oxidative phosphorylation. So the underlying design here is it's all based on real data done now several years ago, using isolated mouse liver mitochondria in a seahorse XF24, which is the old model that's now defunct or just about defunct. But the principles are all the same for the modern machines. And those principles, if you haven't used or don't plan to use the seahorse, also apply just the same pretty well to any other way of measuring the oxygen consumption using an ammeter type machine, such as an Ouroboros or Clark electrodes or various fluorescence systems. So for example, we gave this course in Copenhagen, I think 2 years ago, to a group that didn't use seahorses at all, but had a lab with some ridiculous number like 28 Ouroboroses set out so that they could do a whole range of parallel assays. You need that many to compete with a 24-well seahorse plate. And the principles were all fine. We had no difficulty in discussing it. So these principles apply to any platform of measuring these fluxes. And I left this out of the deck you got because it gives you the answers to all the questions. So the experiments were designed by me in collaboration with various people at Seahorse and with Anne Murphy at UCSD. And they were actually carried out by George Rogers, who was involved in the design also. And we published them in this paper, which you can find on the web. But please don't do that now, because it includes the answers to all the questions we're about to discuss. So if you do it, it becomes a kind of futile exercise for us all. But afterwards, if there's things that you feel you didn't get out of this practical session, then please go to that paper and read it, and hopefully that will address any of the issues that you have that you might have missed in the live session. So we're going to, first of all, talk about experiments designed to look at electron flow in isolated mitochondria. So if we want to look at electron flow, here's the whole system as set up by David. So I just stole this slide from him, where you have NADH being oxidized by complex 1 or succinate being oxidized by complex 2, feeding electrons through the restricted chain through complex 3, through cytochrome C, through complex 4, pumping all the protons out, and then the protons running back through the ATP synthase to make ATP from ADP and phosphate. In addition, there are native leaks, and there are various other things going on, like calcium movements across the membrane. And if we want to investigate electron flow, this system is too complicated. We need to get rid of some of the parts of the system that otherwise would carry control, so that we can focus all of the control over oxygen consumption rate onto the electron transport chain. So one way to get rid of the rest of the system is to inhibit the ATP synthase with oligomycin. So that's the classic inhibitor of the ATP synthase. It prevents proton flow through the FO part of the enzyme. So the whole complex is inactivated and can't do anything and disappears from the picture. So that gets rid of any control that ATP synthesis might have over the rates in this experiment. But we still have the proton-motive force, we still have the proton pumping, and that makes things difficult because we are going to see rates change as the proton-motive force changes. For example, the difference between state 4 and state 3 would still be apparent, or at least between state 4 and state 3U, the uncoupled rate. We can get rid of the proton-motive force by adding excess of FCCP to drain away all of the protons that are pumped out. So effectively, they don't exist. Because we've brought their control of anything to do with protons moving across the membrane to close to zero by having an excess of FCCP, it's like the proton circuit doesn't exist because it's always in excess, and we can always run the electron transport chain at any rate we want, and it's not limited by that proton-motive force generation or dissipation. So by adding oligomycin and FCCP, particularly the FCCP, we've now simplified the system to only electron flow. And that's what we're trying to measure in this experiment, is electron flow. So we can take isolated mitochondria, we can give them some source of electrons that they can use to feed the NAD pool and reduce it. And then those electrons will flow down the chain through the Q pool to complex 3, or from succinate through the Q pool to complex 3, and then on down to oxygen. Question? Just somebody not muted. And then one of the advantages of using mitochondria is we have a whole range of inhibitors and different substrates that we can add to this system. And a lot of the practical is going to be based on the use of these different inhibitors and substrates. So we can feed in blue here, we can feed electrons in at NADH with pyruvate and malate, or we can feed them in with succinate to complex 2, and they go on down the chain. Or we can feed them into cytochrome C using ascorbate, which is vitamin C, an entirely artificial substrate, but really helpful in these experiments. And TMPD, which is just a chemical which is able to ferry the electrons from the ascorbate to the cytochrome C. So by adding ascorbate plus TMPD, we push electrons into cytochrome C, and they can then run down the chain to oxygen, and we can measure it as the oxygen consumption rate, the OCR. And then the big red crosses are the various inhibitors that we have of the different complexes. So one of the nice things about working with mitochondria is the pharmacology is really brilliant. That nature has found great use for making poisons that kill competing bits of nature. So most of these are produced by one species to kill off another species, which is why they're mycins, because they're produced against fungi and yeast and things like that. So rotenone is the classic inhibitor of complex 1. It binds in a way that affects the Q binding site, so the ubiquinone can't get in and pick up the electrons. So it renders complex 1 dead in terms of forward electron flow into the Q pool. There are inhibitors of succinate dehydrogenase. We're not going to be using them, I think, in this practical very much. But the classic one is malonate, which we can use to compete with the succinate, both for transport and for oxidation. The classic inhibitors of complex 3 are antimycin and mixothiazole. They work at slightly different sites, but we're going to be using antimycin in these experiments to prevent electron flow through one of the Q sites in complex 3. And azide is the cyanide equivalent. It's a bit easier to handle and a bit less toxic, so we prefer it over cyanide in many experiments. And it's able to bind to the heme in cytochrome oxidase. And when it binds to the heme, it can't bind oxygen. So again, you can block electron flow through complex 4 by having azide present. Oligomycin, you're now very familiar with. As I said, it blocks the FO channel for the protons and stops the ATPase from being functional either in forward or reverse direction. And the second experiment we're going to be basing this on is an experiment instead to investigate coupling. So in the first one, we simplified the system so that all the control went on to electron flow. In the coupling experiment, we're much more interested in the ATP synthetic ability of the mitochondria and the ability to maintain a proton-motive force and to have that proton-motive force determine the rates. So we need to set the experiment up differently. So here's the basic setup again, but this time what we want to do is simplify so that the control is all in these parts of the machinery, in the ATP synthetic machinery and in the proton circuit. So one way we can simplify is just get rid of complex 1. Complex 1 is susceptible to a bunch of different insults. It tends to misbehave. So if we add rotenone and we don't add any substrate to feed the electrons into NAD to make NADH, then it's inactive. And instead we can just feed in succinate. Succinate tends to be a very well-behaved substrate, gives a nice high potential, nice high rate. It's very amenable to this sort of experiment. So let's drive oxidative phosphorylation using succinate as a substrate in the presence of rotenone to keep complex 1 quiet. And then we can, again, manipulate the rate of the proton circuit either by adding ADP so that we drive the ATP synthase, that drives the proton circuit faster, and that drives electron transport faster, and we can pick that up with the oxygen electrode or the seahorse as an increased oxygen consumption rate. Or, of course, we can add uncouplers, which do the same thing. They dissipate the proton matter force, change all the equilibria of these force flux relationships, and drive oxygen consumption by complex 4. So that's the background, and we'll go through each of those experiments in a moment. And then the main aim of this session is for us to do experiments using unknowns which affect some part of the oxidative phosphorylation system. And then we're going to throw it open to you to tell us what can be said about what those unknowns might be doing and possibly what they actually are. So for the 1 or 2 of you who haven't used the seahorse, this is the XF24. The way it works is that you have a 24-well plate. You spin out mitochondria so that they sit at the bottom of each of these wells. You bung it in the machine and press go, one of these knobs on here, and it runs a pre-programmed cycle of mix, measure, and repeat. And when it's mixing, or when it's not actually measuring, there's a plunger, which are these green spikes here, which are held up by a system, essentially springs, away from the well, so that oxygen is in contact with the surface of the liquid in each well, and you can get oxygen exchange with the atmosphere, which is just atmospheric. It's not controlled in any way. It's just sitting in air, room air. In that condition, you can inject things through these ports under the program. So you can inject at any given time from port A, and you squirt whatever you've loaded into port A into each well, and it mixes in. And then there's a mix phase where this plunger goes up and down, and that kind of stirs everything up and mixes it up together. And there's a mechanical bit. You have to make sure that you don't overdo that, so you don't disrupt the monolayer sitting at the bottom here of the well. And then during the measuring part of the cycle, the plunger comes down, so it's pushed down by mechanics inside the machine to press these green spikes into these wells. And there's bumps on the bottom of the well which contact with the plunger that's coming down. And when they're in contact, that defines a very small trapped volume over your biological material, the cells or the mitochondria that are in there. And assuming that this is oxygen impervious, then what will happen is the biological material will be consuming oxygen, and it'll deplete the oxygen in this tiny trapped volume here, which is just a few microliters. And that's monitored by sensors on these plungers. So there are light paths leading to fluorescent spots on the probe, and they're able to read what the oxygen is and what the pH is within this trapped volume. And then at the end of a measuring period, up comes the plunger. There's a bit of mixing goes on, and everything re-equilibrates back with the rest of the solution and with the atmosphere, so you can reset everything back to the initial condition. And then at a later point, you can push the plunger down again, do another read, and you can do that in principle as long as you want. You can go for days measuring at different intervals to get time courses of what's going on. And then part of the problem in the system, was that a question?
Yeah, I noticed there's 2 sensors.
One is for oxygen, and the other one is for acid, for pH. So you can measure both simultaneously. Most often people just look at the oxygen sensor trace, but one of the points we're going to make in this set of practicals is it's really helpful to look at the pH trace as well, to work out what's going on in your well.
Thank you.
And then one of the problems is oxygen dissolves in this plastic. So a lot of the problems we'll discuss are to do with keeping that properly under control. In particular, when this well goes very low in oxygen because the biology has moved it, has consumed it all, then oxygen comes out of this plastic around here. And when you mix, you now have an oxygen depleted plastic. So when you put the plunger down again, that plastic can suck up the oxygen out of the well and give you false readings of rates. So we'll talk about that as we get to it. Here's the design of the experiment. So First of all, you set up the cartridge at the top. So you make up the various additions that you're going to add to the ports. You add them into each of the 4 ports by each of the 24 wells. You put it in the machine, and there's a calibration procedure that we don't have to worry about here, which just calibrates the probes. And then in the other part of the experiment, you set up the plate itself. So seed cells into plates, or in this experiment, we're putting mitochondria in. So we just put a glob of mitochondria into each well. And then because the machine mixes between experiments, you need the biological material to be stuck to the bottom. Otherwise, it just mixes into the whole volume of that's in the well and dilutes out the signal, and you lose your signal. So to stick the mitochondria down, we just give them a brief centrifugation, which slightly surprisingly, they don't seem to mind very much. So the mitochondria form electrostatic interactions with the plastic in the well, we imagine, through their outer membrane. And slightly to our surprise, they stay stuck, they don't break, and they don't seem to mind very much what's going on outside the outer membrane. And then to do the experiment, you set up the initial conditions with whatever substrate needs to be in the plate, put it in the machine, it comes into contact with the cartridge and forms the whole setup. And then you run the program, and it reads out the 2 different channels for each well for what's going on in terms of oxygen and for pH, or the rate of change of oxygen, OCAR, or the rate of change of pH, which they call ECAR, extracellular acidification rate. And here are the 2 experiments set up in that way. And what we're going to do is present you unknowns for each of these experiments. So you'll get the data for what happens in the electron flow experiment and in the coupling experiment for a bunch of unknowns. But as the setup for that, I would want to go through each of them in turn, just to try and understand, or get you to help me to explain what's going on in these experiments as we make all the different additions. So we'll start with the top one, which was the electron flow experiment, which, as I said, we set up by having in the medium before we start, we add the substrates pyruvate and malate, and we have a coupler there, FCCP, and I think there's oligomycin. It turns out not to matter very much whether it's there or not, in order to prevent any effects of the protomotive force, and we're just concentrating on the electron flow in this experiment. So conventionally, with isolated mitochondria, we add pyruvate and malate together. So the first question to get us warmed up for you guys to just shout out from the floor is, why would you add 2 substrates mixed together? Why make life complicated when we've been stressing all the way through up to this point? The whole aim here is to simplify as much as possible. So why are we adding a mixture of 2 different substrates rather than just malate or just pyruvate? Just shout out from the floor if you think you know the answer.
Do you need,
make sure.
Sorry, go ahead.
To make sure there's enough fuel to maintain that boundary of the system?
Yeah, so you have to have plenty of electrons in a form that the cells, or the mitochondria in this case, can use. But the specific question here was, pyruvate dehydrogenase will reduce NAD to NADH, or malate dehydrogenase will reduce NAD to NADH. So why add both? What's the point of that? The kinetics of those enzymes are fast enough so that either of them would reduce the NAD pool perfectly satisfactorily.
So you don't get product inhibition?
Yeah.
You can't consume the malate without making oxaloacetate and citrate, right?
Yeah, that's right. So do you want to make that a bit clearer to the rest of the audience?
Pyruvate in PD8 and pyruvate dehydrogenase becomes acetyl-CoA, and then acetyl-CoA and oxaloacetate that comes from malate both become citrate. And so if you don't have both of them and you can't make citrate, then you have no pathway for the malate or acetyl-CoA to escape. And then you'd have a buildup of both of those, or either of those, I guess, and then product inhibition that prevents you from making NADH.
Yeah, beautifully said. I couldn't have said it better. So if you add just pyruvate, what happens is the pyruvate goes into the mitochondria, pyruvate dehydrogenase takes CoA and NAD and makes acetyl-CoA and NADH. And if you don't do anything else, there's nowhere for the acetyl-CoA to go because there's not much oxaloacetate in mitochondria to consume it to make citrate in the Krebs cycle. So the acetyl-CoA builds up and it turns out acetyl-CoA is a really good inhibitor of PDH. So it's a good feedback inhibitor. So it runs and then it stops running. So your oxygen consumption takes off and then it stalls and everything stops. Conversely, if you add malate, again, malate gets into the mitochondria on a carrier. Malate dehydrogenase is a very active enzyme, so it reduces NAD to NADH, and the product is oxalacetate. But if you don't provide some acetyl-CoA or some other way of getting rid of the oxalacetate builds up. And you get a mass action effect. So the equilibrium of malate dehydrogenase is in fact way over towards malate. So once you've made a little bit of oxalacetate, the enzyme comes close to equilibrium and stops. So it reduces a bit of NADH and then it stops. So you get a rate and then the rate gives up. But if you add the two together, then each of them provides the thing the other one is missing. So when you're using pyruvate, the malate can be considered just as something that provides the oxalacetate to allow citrate synthase to work to make citrate, which is just kicked out of the mitochondria, and recycle the CoA that you need for the PDH to run. Or you can consider it the other way around, that when you're using the malate as the substrate, the oxalacetate that's generated, the PDH just provides the acetyl-CoA to mop up that oxalacetate and again make citrate. So when you have both together, it's a long-lived steady state where the malate and pyruvate going in, both of them reduce NAD to NADH, which is coupled to the electron flow and the reaction that we're measuring. And citrate synthase converts them into citrate, and the citrate's kicked out into the medium. So there's an infinite amount of medium as far as the mitochondria are concerned. So they go from an infinite pool of malate and pyruvate, and they dump citrate into that infinite pool. So everything works for a long time in a nice steady state.
Martin, can I ask a question?
Yeah.
I was just wondering, so this is very useful in vitro, but is there a physiological significance of this, or like where malate and pyruvate are coming from in vivo? When would this become relevant?
So the main place where you see it in vivo is anaplerotic reactions in the Krebs cycle. So under some conditions, you can deplete the carbon in the Krebs cycle. And then when you give cells glucose, they put pyruvate in and make acetyl-CoA, and then this situation arises. And so you have anaplerotic reactions that are able to pick up carbon from elsewhere and put it into the Krebs cycle to make the oxalacetate. So glutamine is often used for that, or pyruvate carboxylase itself, using the pyruvate, it can be directly carboxylated to oxalacetate to start the Krebs cycle and make it run. But it's not unusual to find a situation where your oxygen consumption by a cell is limited, and the reason it's limited is not enough Krebs cycle intermediate to run this system.
Mm-hmm. And what, I'm just thinking, so malate's only going to come from the Krebs cycle. So what situations, I'm just thinking of disease situations where that would be limiting and where this has been used practically, or, sorry, I'm going off topic, but just, this seems very interesting.
Yeah, so what we're trying to do here is an artificial system to power electron flow. So we're not trying to do physiology. So it's not designed for that. Of course, malate will appear in real life from the Krebs cycle and from the breakdown of a few other metabolites. But generally, it's not an independent variable in cells. It's always linked to the Krebs cycle. So it's not particularly physiologically interesting as a substrate. I think that's right. Would you agree, Shona? I put Shona on the spot. Okay, she agrees. Okay, good.
Sorry, yes, I agree.
So we put in a mixture of pyruvate and malate just so we get a nice steady source of NAD reduction to NADH, and we can then feed the electrons into the electron transport chain.
Martin,
So that's
I have a quick question.
Yeah, please.
Why do you need to kick out citrate just to maintain the charge of the mitochondrial prep or something?
These are relatively high fluxes, so we're taking up quite a lot of malate and pyruvate. So we're making quite a lot of citrate. If it was to stay inside the mitochondria, you get an osmotic effect. So gradually the mitochondria would start to swell, and that eventually will damage the coupling, so you'd lose coupling. If you inhibit citrate transport with inhibitors, that's what you see, that after some usually quite long period of time, gradually things start to stop, slow down, because you're building up citrate and you can't get rid of it. So eventually it will reverse the equilibrium here and reverse these equilibria and shut everything down. I think I was going to say sometimes you see the same sort of skin of glutamate plus malate, and that's also used as a conventional substrate with mitochondria. And the principle is the same. You're just using transaminases to make this oxaloacetate from glutamate, and everything has to balance up in a similar way to allow NAD to be reduced continuously. Okay, so we're in this part of the experiment. So we've put the pyruvate and the malate into the well. We've put the plunger down, and then we're measuring with time what's happening. And this is the derivative of the oxygen concentration trace. So it's measuring the rate of oxygen consumption. So this should be flat, shouldn't be decreasing. What you'd expect to see is they're just respiring quietly at whatever state 2 rate these mitochondria are able to run at in the absence of making ADP. And then what happens here in the break is that the plunger comes up, they're given a bit of a mix, and then it comes down again, and we rerun it. And oddly, it starts at the same point as before and runs down again. That's the sort of thing you often see in traces, and we'll come back in more clear examples as to what that's due to in a minute. And then in the electron flow experiment, the first addition is to add rotenone from the first port. So we squirt rotenone into the system, and the observation is the respiration rate drops to 0. So we start on simple. Can anyone explain why did the respiration rate drop to 0 when we added rotenone? Not a trick question, just nice and simple.
You're providing electrons to complex 1, and then rotenone is a complex 1 inhibitor. So there's no longer electrons entering the electron transport system.
Yes, exactly. So rotenone, as I said before, inhibits this Q binding site, or stops the action of the Q binding site in complex 1. So we're pushing electrons in, we're reducing the NADH, they're reducing the iron sulfur centers here, but they can't go anywhere. You can't reduce the Q. So as far as the rest of the electron transport system is concerned, there's no electrons, because there's no way for them to get through from pyruvate and malate into the rest of the electron transport chain. So everything stops because they've run out of electrons. And then we add some succinate in the next port. So we mix in some succinate from port B, and now the rate goes up. So 2 questions here. Why does it go up? That's the simple one. And why does it go up higher than it was before? That's the slightly more difficult one. So first one, why does the rate go up when you add succinate? These are all simple. I would get in and answer these simple questions, because later on I'm going to ask the people that haven't answered questions to answer the difficult questions.
Succinate bypasses complex 1 and provides the necessary components for complex 3.
Yeah, so it's just a straightforward substrate. So it crosses the mitochondrial inner membrane on the dicarboxylate carrier. It's then accessible to the succinate dehydrogenase, makes fumarate, pushes electrons in, they reduce the Q pool, everything runs from oxygen consumption.
I have a question. Why would the succinate level be so much higher than the complex 1, the pyruvate malate?
Yeah, that was my second part of the question. So everything's uncoupled, so this has nothing to do with proton-emitted force, nothing to do with proton pumping stoichiometries. Why would you get a higher respiration rate with succinate than you do with pyruvate plus malate? Again, it's not a trick question. It's sort of kind of straightforward.
Because you're using more?
Yes, because the succinate dehydrogenase, to a first approximation, is just a more active enzyme, so it's able to reduce the Q pool faster than the complex 1 pyruvate dehydrogenase, malate dehydrogenase combination, which isn't able to reduce the Q pool at quite the rate. So the Q pool is maintained more reduced when you add succinate, just for kinetic reasons. And that drives the whole chain, and so you see a faster oxygen consumption rate. So it's just a good example of forces or delta G effects of the more reduced this Q pool is, the faster everything goes. And then we add AA in the next port, which is antimycin A. I think you're getting the idea. So antimycin A slows down the rate. Why would that be?
It inhibits the complex 3.
Yeah. So it's our classic inhibitor of complex 3. So we're putting the electrons in from succinate, they're going to the Q pool, but when they get to complex 3, the complex 3 is inhibited with antimycin, which is binding at one of the 2 Q sites. And that stops most of the electron flow, or all of the electron flow through complex 3. So the electrons are unable to get through to complex 4 through cytochrome C, so the oxygen consumption drops. One of the little quirks here is it doesn't drop quite as far as it did with rotenone. And that's an example of one of the things that David and I missed for about 3 years of doing this course. And then we realized, of course, this is a real effect. This is not just an artifact. Any idea why it might be that antimycin doesn't fully inhibit, but rotenone does? This is a more complicated question.
Is there some reverse electron transport occurring when you inhibit complex 3?
So what you have to do is get electrons to oxygen in complex 4. So reverse electron transport doesn't help because you've got to get oxygen reduced to water. So unless you get electrons to complex 4, you're not going to see anything in the oxygen measuring system. So it wouldn't help if there was some backup of electrons into the rest of the chain. It still wouldn't cause oxygen consumption.
Are you forming Ross?
Yes, that's the explanation. So it turns out that when you inhibit complex 3 at the QI site, the inner Q binding site, you leave open the site where the QH2 comes in, and it's able to go into that site and make a semiquinone. And that semiquinone has got nowhere to go because you've inhibited the other site in the Q cycle. So eventually an oxygen will come in and pick off that semiquinone and make superoxide. So under these conditions of antimycin, there's superoxide production into the matrix and also to the outside. And that superoxide is actually a good reductant of cytochrome C. So electrons are able to go into this site, which is open but can't do anything, and then hop back out again and go onto cytochrome C and then onto the cytochrome oxidase and cause this small oxygen consumption rate. And so that is actually a representative rate. That rate represents the 3QO, the complex 3 Q site superoxide production. And you can see compared to the fluxes through complex 3, it's pretty low. So it's so low that David and I missed it for the first 3 years. But it's a real rate. So there's a bypass around complex 3 caused by that superoxide production. And if you use mixothiazole, the reason I know this statement is probably true, mixothiazole binds to the QO site, the one that's responsible for this leak of electrons. And if you use mixothiazole, this comes down to 0. So they're different. So it's one way of manipulating mitochondrial superoxide is to compare what mixothiazole does with what antimycin does. One of them stops electron transport, but makes a lot of superoxide. And the other one stops electron transport and superoxide production. Of course, stopping electron transport isn't a particularly good thing to do if you're trying to look at some physiological response of a cell. So it's a dangerous tool, even though it can be used.
Martin, I had a question related to this. We found with just rotenone and annamycin A as the conditions for isolated mitochondria that we see high superoxide production. I was wondering if you could explain for us why that might happen if there's no electrons entering the electron transport system.
I'll cover that in the lecture I give on Ross production, but it depends on your conditions. I presume you've got some complex 1 substrates in there, have you?
No, it was, it's only with rotenone and annamycin A.
Then it's not quite so clear cut, but I would still offer the same explanation, which is there's enough endogenous substrate production to run pyruvate dehydrogenase and oxyglutarate dehydrogenase as Ross produces. And when you add the rotenone, you block any flow of electrons there, so those sites reduce and they start to generate superoxide or hydrogen peroxide. That's a guess. It's certainly the case if you add pyruvate or you add oxyglutarate. It's arguably the case if you don't. But in the presence of rotenone, this flavin site of complex 1 is open, and that does have a low rate of superoxide production as well. So that would be another contributor. Again, you have to invoke endogenous substrates to drive it, which is a guess in this particular instance. But electrons generally have more difficulty getting into this part of the chain. So you wouldn't expect it to be from complex 3, just because there's no easy way to get the electrons in. There's easy ways to get the electrons into this part of the system from endogenous substrate. Okay, where did I get to? So then we can add ascorbate TMPD and we get a high rate again. So if you can't get this, you should really consider retiring. Anyone?
The ascorbate via TMPD is providing electrons to cytochrome C, and so the rate can increase again.
Exactly. So I just told you it. So if you were listening, ascorbate's not particularly used by mitochondria, but it's very handy in these experiments. TMPD is a catalyst, picks up electrons from ascorbate and puts them onto cytochrome C, and so now they can run into cytochrome oxidase, even with all of these other inhibitors and the substrates no longer matter, present still in the system. So we get this high rate. And it turns out that that rate depends on how much TMPD you put in, so you can get it to go higher if you add more TMPD. And we've just used a sufficient amount to stay in the range of the normal substrates, the succinate and the pyruvate malate. But we could make that rate go faster if we wanted to. So I just looked at the oxygen trace. There are also interesting things going on in this parallel pH trace. So let's just step through them. So we set up the system at pH 7.3, nothing much is happening, And then when we add succinate, there's a sudden shift to the alkaline by, 0.15 of a pH unit. Any thoughts about that? What might that be? Why do we get this alkaline jump when we add succinate in the presence of rotenone and pyruvate malate?
We're pumping the protons.
You're using the protons.
So everyone thinks about protons. Remember how we've set this system up. We've made sure that protons don't matter.
Oh.
We've uncoupled it, we've oligomycin inhibited it, so that the proton cycle really is irrelevant. So it's nothing to do with that. I'll just let that ring, sorry about that. This one is in fact trivial, and again, it is one reason why one should always look at the pH trace. When we made up the succinate, we made it up to alkaline. So when we squirt in a weak acid, succinate, which is a pH buffer, which is too alkaline pH, it shifts the pH of the system to the more alkaline. So it's just bad experimental design on our part that we didn't pH the succinate right. And the reason I'm highlighting is that that's really quite a helpful thing to know when you're running these experiments, that you made up your solution wrong. So always keep an eye on the pH trace, because if you get things that suddenly go to pH 3, it's because you had a very acid addition and you forgot to neutralize the phosphate. So you just added phosphoric acid and everything died. And the explanation for why the rates all die is completely trivial. You just acidified it and all the proteins denature. But you see it in front of you in the seahorse. So have a look at it and you can put things right. So the next time we run it, I hope we neutralized the succinate properly and it didn't change pH. And you can see when we did the mix, which mixes in the rest of the solution, that diluted out the succinate, so the pH dropped back towards where it should be as we mixed in the rest of the contents of the well. And then the final one, which is actually a bit more interesting, when we add the ascorbate TMPD, there's a slight shift in the baseline, which again might be that our solution was a little bit acid. But now we seem to see a rate. There's a rate of alkalinization when we add the ascorbate TMPD. And that one is meaningful, it turns out. So I'll ask if anyone knows what it is, but you probably don't. So I'll quickly move to the solution if no one offers an answer.
Does it have to do with the ascorbate as an antioxidant?
Not overtly, although it might be a little bit related to that. In this case, you have to think about what reaction are we driving, and ascorbate's just a bit odd. So ascorbate is singly charged, and when it hands on electrons, it hands on 2 electrons to TMPD, to 2 TMPDs, to reduce the TMPD. And that gives you dehydroascorbate, and it dumps 1 proton in the process. So this is what David would have told me you can't talk about as a hydride transfer. And then those 2 electrons flow down the chain, and when they finally end up at cytochrome oxidase, they reduce half an oxygen to water, so you need 2 protons to make that water. So 2 protons disappear here, 1 proton appears here. So the net result is every time you run a pair of electrons from ascorbate to oxygen, a proton disappears. And that's the alpha ionization. And you can actually measure it, calculate the buffering power, work out how much ascorbate is being used, and you can see that that agrees with how much oxygen is being consumed. And that acts as an internal check that everything is behaving exactly as it should. So the experiment wasn't designed to show that, but it's to illustrate that various of the reactions that you do, not only are pumping protons and doing things of that general vectorial sort, but there are also underlying scalar reactions going on where you're changing the pH due to the chemistry that you're running. And this is an example of that, where the chemistry that we're running has a net effect of removing 1 proton every time 2 electrons reduce oxygen. It wouldn't be true if the ascorbate made a product that released 2 protons. So if we replace this by succinate, which makes fumarate plus 2 protons, then you don't get that effect because it's pH balanced. You only get it because of this peculiarity of the pKs of ascorbate, where you only get a single proton released when 2 electrons are removed from it. Okay, so that's the electron flow experiment. We understand why we see all these rate changes in the control. And what we're going to show you in a while is an experiment where we have an unknown present, and some of these things behave differently. So you're going to use this control, which you now understand, to interpret why the experimental behaves differently.
I have a very basic question.
Go ahead.
Hi, I'm Jian. Does it matter the order of the substrate addition or the drugs? Is it important? Can you swap the orders? Is it okay?
So what if we added antimycin here instead of rotenone?
Yeah.
What would be the effect be when we added the succinate? So antimycin inhibits here. Once it's present, if you add succinate, you can not get the electrons through to cytochrome oxidase. So if you'd added the antimycin instead of the rotenone here, everything's dead until you get to the ascorbate, when you can finally get the electrons running again. So it does matter, absolutely it matters. This is a sequence of feeding electrons upstream, stopping upstream, moving down a bit, put electrons in and then stop them, move down a bit, put electrons in and stop them. And if you change the sequence, you screw the whole experiment and you lose a lot of the information. Or you can interpret what you've added is the other way of looking. So yes, it matters what the order is.
I have a question, going back to the last one. So with the addition of the sorbate, I thought I wouldn't expect that much of a pH change because of the uncoupling agent at CCP.
Okay, so I didn't make it clear then. There are 2 sorts of protons in this system. There are the protons that you get excited about, which are the pump protons, the vectorial protons. When they're pumped across the membrane, that causes a pH difference and a membrane potential across this membrane. And they are the force that drives ATP synthesis. So they're really important for all of the function that we care about. But it turns out that the pH changes in the medium are trivial. If you set up half a pH unit across the mitochondrial membrane in a big pool of buffered medium, you just don't see that change. All of the change takes place in the matrix where you can't see it. The pH change outside is trivial just because of the dilution into the buffer. So you never see these vectorial pH changes in the medium in the seahorse. Instead, what you see is the boring bit, which is the underlying chemistry, which I illustrated here, which is if you run a net chemical reaction where you're pulling electrons of ascorbate, putting them onto oxygen, and in the process, you use the proton every time you run that. And gradually, more and more protons get used up. Gradually, the pH in the whole medium changes, and you drive the scalar reaction, and you can see scalar reactions.
Got it.
So the pH changes are always scalar reactions. The sensitivity just is not great enough using extra mitochondrial pH sensing to ever see the pH gradient. If you have a pH probe in the matrix, you could see it, but you don't have that. Okay. So that's the electron flow experiment. Now let's put our attention to the other side of the experiment, the coupling experiment. So this is the one where instead of concentrating on the electron transport chain and the cytochrome system, we're now just trying to understand the proton cycle and the ATP synthetic cycle. So here's that coupling experiment, and here's the interpretation of what's going on. So in the medium, we put in rotenone and succinate. So we've stopped complex 1. We just don't need to worry about it. And we're driving everything with succinate oxidation. And as the electrons flow down the electron transport chain, they go through the 2 proton pumping complexes that are now available, complex 3 and complex 4, pump out protons, set up a proton motive force, and that drives either the ATP synthase or the native leak in the membrane, or if we are uncouplers, they'll drive the uncoupled leak. So we set it up with succinate and rotenone, and we get a rate, and this is the state 2 rate, similar to the optional electrode experiments that I was talking about in the lecture. And then we add ADP, and the rate goes up. And so this is crucial to the whole understanding of bioenergetics, which is, why does that rate go up when you add ADP? So would someone like to volunteer to just go through the logic of why it is that the oxygen consumption rate increases when you go into state 3?
You're driving ATP synthase, so it kind of gives you the same effect as the uncouplers, as you said earlier. Yeah.
So why does driving the ATP synthase cause cytochrome oxidase to go faster?
The supply and demand. Yeah. So it's like it's driving because it's going down and making more ATP, and then it's driving the electrons. I don't know if I can explain that well.
Yeah, so the bit that's missing is the proton circuit from that explanation. So what you said is true, but it kind of misses one of the key elements in the way the coupling works.
Is it the proton motive force is now driving?
Yeah.
Yes.
So when you add ADP, what you're doing is you're changing the resistance of this pathway. So the ADP is now being engaged by the F1 component of the ATP synthase, being converted into ATP. That's being driven by and allowing a flux of protons across the membrane. So protons suddenly start to pour into the FO to drive this revolving head of the F1. So there's a drain on the protons, which is like David's electrical analogy, short-circuiting the system, and would be similar to what you would do if you added uncoupling. And that drain of protons decreases the value of the proton motive force, because you're now demanding more than you're providing. So its level drops. And the electron transport chain, sitting there quietly minding its own business, suddenly sees that the back force against which it's working has decreased. So by these mass action delta G effects that we've been talking about, they're now pushed away from equilibrium. So they were close to equilibrium. The oxidase is never at equilibrium, but complex 3 is often quite close to equilibrium. In either case, they're pushed further away from that equilibrium. So by the principles of irreversible thermodynamics or mass action, depending how you look at it, they go faster. So these pumps run faster. Electrons therefore run faster because the proton pumps are being driven by the electron flows. So electrons start pouring down to cytochrome oxidase, and oxygen consumption increases, and then you see the increase in the rate. So that's the critical modern interpretation of the chemiosmotic theory. That's what this whole course is about, is that mechanism. Why respiration is coupled to ATP synthesis, and why you can use a seahorse to tell you about ATP synthesis in a cell. It's because they're coupled together by this mechanism. And if you interrupt the coupling by adding uncouplers, then you disrupt that relationship, and the information you get suddenly changes in its meaning. Let's switch across to the pH trace.
Quick question, Professor Brandt. So the values when we after adding ADP is much less when you compare with succinate. Why the level of the value for OCR on the y-axis? When I compare with the previous one, after adding succinate, I can see going to the,
Yes, it's about twice as much with succinate as it is with ADP. I think the conditions are equivalent. There's normally a small difference. It's normally not that big. So normally you would see, this is an uncoupled rate. So normally you'd see a rate that went up 10 or 20% when you had uncoupler compared to state 3. Here it's up a lot more than that. I have no idea why. It might be they're not paired experiments. It might be they were done at different times with slightly different preps, but you're right, they should be more similar than they are. So,
The top one has FCCP initially, so wouldn't that change kind of a maximal oxygen consumption of the system?
So this comes down to the kinetics of the ATP machinery. And in mouse liver mitochondria at 37 degrees, which is what this is, those maximum, the rate of, what's the right way to express this? The drop in proton motive force caused by the addition of ADP and the drop in proton motive force caused by the addition of excess FCCP, although they're very different, in both cases, the electron transport chain is running pretty close to its Vmax. So it hardly responds to that extra drop. So that was apparent in the kinetic curves that both David and I were showing. Once you get to state 3, there's a horizontal line, and dropping the PMF hardly makes any difference. That's an expression of this. So what you would expect is, because the chain is going pretty well at Vmax, even with ADP as the substrate, then when you make it go at Vmax by having uncoupler there in the presence of succinate, it doesn't go very much faster. That is not true under some other conditions. So if you do the experiment at 25 degrees, the adeноnucleotide carrier becomes really quite rate limiting, and you can get much bigger effects of uncoupling. But at 37, it's generally pretty much the same. So that was a good and astute observation, which I haven't got a really clear answer.
No, I was thinking that because when you give succinate as a substrate, then it goes through the ubiquinol synthesis, right? So whereas with ADP, it doesn't go through that. Does that can affect any of the OCR rate actually?
So remember where we are. So in this coupling experiment, we've got succinate and rotenone in the well, and then we're the rate after ADP addition. In the electron flow experiment, we've got some pyruvate and malate there as well, which probably shouldn't matter very much. And then we've got rotenone and succinate. So it's pretty much the same condition as this, except that here you've got FCCP present and here you've got ADP present. So there is always a small limitation of the rate with ADP compared to the maximum rate. What I'm saying is it's not usually this great. So I don't quite understand why this one's so much faster. Maybe they were just not paired experiments. Okay, so where have we got to? We added the ADP, we saw this increase. It's really important. This is the mechanism of coupling of oxidative phosphorylation. Just switch across to the pH trace. Again, we see this, not just a jump in pH to a new value, but there's clear rates of alkalinization when we add ADP. So it's not that we made up the pH wrong. There's some other explanation. Anyone got a suggestion for why do you see a pH change after the addition of ADP? And remember what I said about the pumped protons is that you never see them. They're just diluted into the medium. So this is not to do with proton motive force.
Could it be because kind of piggybacking onto the previous question, the answer for the previous question where you increase flow through the proton circuit when you add ADP, you have more electrons passing through and water accepting more, or sorry, oxygen accepting more of the electrons, and that's where the protons are being taken up. So pH drops or increases, I guess.
If that was true, you would see it here, right? So here you've got FCCP present because we added it in the well, and you've got rotenone and succinate. And there isn't a rate. There's this artifact of not getting the pH right. I mean, you could argue about if there's a rate, but if you do the experiment repeatedly, there isn't a rate here. So simply having rapid electron flow from succinate doesn't change the pH. The reason it doesn't change the pH is it's balanced. So the succinate produces fumarate plus 2 protons, and all the proton pumping and everything else takes place. And then those 2 electrons reduce half an oxygen to give you a water, and use 2 protons. So these 2 protons are formally used again here. So there's no net pH change.
Is it the phosphate consumption in generating ATP?
Yeah, good. Do you want to explain?
The phosphate is generally acidic. So if ADP plus phosphate reaction, when the proton pump is running, would produce ATP and remove the big equation that David had initially with HPO4 minus. And
Exactly. So David mentioned that in his equation for ATP hydrolysis, there's a proton in there. So if you hydrolyze ATP, you actually change the pH. And it's a bit more complicated than his simplified diagram. So this is what's probably happening during ATP synthesis, the reverse of the ATP hydrolysis. So ADP plus H2PO4 minus gives you ATP4 minus. So this is charge balance, 4 negative charges on this side, 4 negatives on this side. These things are related to magnesium, of course, but that doesn't affect the overall argument. And the pK of phosphates is roughly 7 for the interchange between the 2 minus and the 1 minus form. So when at about pH 7, you remove one PO4 1 minus, that gets replenished from the pool, and you take half of a 2 minus and half of a 1 minus to make the replacement 1 minus. And that consumes half a proton. So as you go from the 2 minus to make the 1 minus, you use half a proton, and roughly half of it comes from that pool and half from this pool. So the net result is you use half a proton at about pH 7 when you make ATP from ADP. And so you get an alkalinization. And it's a net scalar reaction. We're converting 4 millimolar ADP into about, over this time course, a couple of millimolar ATP has been made. So we've got a large scalar change in protons by a couple of millimolar, which is enough to change the pH noticeably in this buffering system. So this is actually a direct measure of ATP synthesis rate. And you can use that to, if you know this relationship here, you can calculate the ATP synthesis rate. And since you have the oxygen consumption rate in the same experiment, you can calculate the P2O ratio, for example, and show that all of that argument is correct and that everything fits together, and that you get the correct P2O ratio for the particular substrate that you're running. And if we did add oligomycin, but we added a respiratory poison at this point, then this would reverse as the ATPase is chewed up the ATP it had made, and the thing regenerates those protons and it goes back to the base order.
So Martin, is that the entire explanation, or is it that NADH with the succinate present is continuously sopping up protons, or would that not contribute?
So you may have noticed I drew my NADH differently from David, and it was exactly to cover this point, that although normally it's written as NADH goes to NAD plus a proton, that confuses the issue. Because the net reaction is, if you make that NADH from a dehydrogenase, it's 2 protons that's involved, and it's just the peculiarities of the pK of NAD that makes it appear that it's a 1 proton transfer. So connecting it back to whatever it is that reduced it, it's actually a 2 proton reaction. So I wrote it here formally as NADH2 and NAD plus 2H plus, just to make the point that these 2 protons, when you're running from NAD down to oxygen, are the same as the 2 protons you use to make the water, and there's no net reaction. Right. So when you start with, if you started with NAD in the test tube, you would see a pH change, but we actually start with pyruvate and malate, and that's all balanced for protons, so you don't see any changes. So Thanks. It was the whole story, as far as I know. Mm-hmm. Things are never the whole story, but I don't know the complication then. Okay, then back to the mainline experiment. So we had a rate of oxygen consumption, the state 3 rate, and we added oligomycin, and the rate drops down to the state 2 rate again. And again, you should by now be pretty clear about that. So why does it drop down?
You block ATP synthesis and there is no flow.
Yeah, so it's like taking away the ADP. I've gone out of sequence a bit. By adding oligomycin, we stop this cycle, and therefore we've gone back to the original condition like it was before we added the ADP. We're in a state 2, where everything is limited by the proton motor force. So these complexes go slow because they're working hard against the proton motor force that they've built up. And you're no longer dissipating it, because the oligomycin prevents that. I think I'm a little out of sequence, so I apologize if I get this slightly wrong, but the next thing we do is we add FCCP and we see a high rate. And you're happy about that. So by adding FCCP, we increase the leak. It's like having ADP in the absence of oligomycin, so we see the same thing. We get the same high rate as we did in state 3. And then you're going to complain that this doesn't look like state 3, right? It's doing funny stuff. So this is one of the teaching moments. Yeah, it's doing funny stuff. And this is a problem of the seahorse. And it's a problem of not using the seahorse correctly that made that funny stuff appear. So what I gave you was the theory of what you should see, which is a steady rate, which is about the same as this, or maybe a little bit higher. It's the one we were talking about where before it was high and about here. But now it's dropping with time. So you have to think about what's going on there. And I realized why I got out of sequence, and it's because I missed making a point about the ADP. So let me make the point about the ADP, and then I'll come back to that point. We were very puzzled when we first started that we had to add a bucket load of ADP. In a Clark electrode, you don't. You just add a little bit and everything goes and then stops. And we realized after quite a long time that what we're doing here is we're trapping a tiny proportion of the total volume in the well that we're measuring. So the whole volume might be 700 microliters, and we might be trapping 7 microliters in the chamber where we're actually measuring. So although we've got 4 millimolar ADP in there, which is whatever it is, 4 nanomoles per mil, we're only using 1% of that trapped in the volume. So it doesn't take long to run out. So you have to have a lot so that in the trapped volume there's enough not to run out in this relatively long 10-minute period while we're running them in state 3. So in this experiment, what George did was just to add different amounts of ADP and follow what's going on. So if you add 4 or 2 millimolar ADP, then you see the state 3 rate, which is persistent because it doesn't run out across the whole course of this, whatever it is, 10-minute incubation. But if you have slightly less ADP, 1 millimolar or half millimolar, then it runs at state 3 just fine, but it runs out and you go into state 4 and the respiration rate collapses. And if you add less ADP, it collapses sooner. And if you add a small amount, which is about the amount you would add normally in a Clark oxygen electrode experiment, it goes and then it's all over and it collapses down. So this is going into state 4 and it goes back into the state 4 rate. And in this representation, where we show each point of the curve, it's pretty obvious what's going on, so you won't get confused. But what the seahorse let you do in the old XF24s, and I think by default does in the current machines, is it averages all these points to save you the time. And if you average all these points, you get completely misled about what's going on. So what it seems to be is there's a strong concentration dependence on ADP with a Km of somewhere between 0.5 and 1 millimolar. So you would infer from this experiment that the Km of mitochondria for ADP is about millimolar. And it's not, it's way, way less than that. And that's a fault of the way the seahorses averaging together these different rates during the time course of the experiment. So for this blue point here, it went at the state 3 rate or thereabouts for 30 seconds or a minute or two. And then it dropped down to the state 4 rate for the rest of the time, and all of them are averaged together. So you think there's a low rate, but there isn't. There's a mixture of a high rate and a standard low rate. And the ratio of those two things varies as you vary the ADP. So 2 things from that. One is you need to make sure there's enough reagent in the well if it's a reagent that's being consumed, so it doesn't run out in the time of your measuring before you remix. And the other is you need to make sure that you're displaying the information in a way that is meaningful. And if you have rates that change between 2 additions, you really have to go into the guts of the machine and lay out the time course of it so you can see what's going on in terms of the rates.
I would jump in, Martin, to add that although this was easy on the old machines, it's still possible on the new machines. So it just takes fiddling with the display options to be able to display all of the measurements during the measurement time period, which is what the left panel here is showing.
Yeah. So the take home here is, if you don't quite know what you're doing with a seahorse, you can get completely fooled by the output and think that you've got something with an affinity which is quite different from what it really is. And the way to overcome that is to just look more carefully at the pH for some of the things, or for the absolute oxygen for some of the things, or in this case, look at the point-to-point mode and just make sure that your rate is actually constant for the full period of the time that you're averaging it and is not changing in time. So that was what I meant to say, which is how I got out of sequence. So that's the rider on that. Now we've got the oligomycin addition bringing us here. We've been through that. And then when you add FCCP, the rates go fast. And where we got to is, why is this behaving peculiar and not behaving as it ought to? So again, George did an experiment. So this is slightly different conditions, so it doesn't match exactly, where he varied the amount of mitochondria in the well. So it's expressed per well rather than mix per mil like the other one. And what you can see is that the system at low mitochondrial concentrations is fairly well behaved. So take them at 5 micrograms of mitochondria, well, even that one's starting to go, but 2.5 micrograms of mitochondria, you're getting a rate, and that rate is more or less okay when you uncouple. But as you increase the amount of mitochondria, say to 20 micrograms in a well, the ADP is starting to misbehave, but the FCCP has just gone crazy. So something's happening as you raise the mitochondrial concentration. And by the time you get to a grossly overloaded well, even the ADP rate is starting to be nonlinear. And now the uncoupled rate is missing the peaks and just giving you some incomprehensible readout. Do people think they know what's going on here, or should I go on to the explanation?
I have a guess.
Go ahead.
Could you be making the well hypoxic at the micro well?
Yes, exactly that. Good. So what you can do, so this is the equivalent experiment, slightly different, so that the loadings are different, but the same general phenomenon. This is done in a way that was particularly bad, so it makes the point. If you switch to just looking at the oxygen tension in the well, and again, in the old seahorses, that was just a push of a button, it was obvious. In the new ones, I guess you could do it, but it's a bit more difficult to find it. Is that right? Yeah.
Yeah, it's not that difficult, but it's not as easy.
So if you look and see what's actually happening to the oxygen tension in the well, as you run, particularly at these higher concentrations here, it's going down to only about 30% of its nominal starting value, and it's starting already a bit lower than the true starting value. It should be up here. And then after you mix and do it again, it's actually going to 0, and it's not quite 0 because of the correction algorithms. So the real 0 is somewhere down here. So that's pretty bad in this state too. It's not so bad if you have lower concentrations of protein. But when the rates are faster with the ADP, then in this experiment, at all loadings, you have a problem. And that problem is you're running out of oxygen during the whole experiment. So of course the rates are collapsing because there's no oxygen there to consume. So that the thing is reporting low rates because there's no substrate, no oxygen left in this case to get the rates. And then, so that's one problem. And then the second problem is if you look at where the highest value is each time, it's dropping during the experiment. So in the lightest loading, you start at maybe 150 millimeters of mercury. It's about the same at the beginning of the ADP experiment, but by the time you get to the oligomycin experiment, it's dropped. And when you start the uncoupler experiment, it's now down to only about 60% of what it was before. And so what's happening here is that in this, as the oxygen tension drops and you get into this hypoxic and anaerobic state in the well is sucking oxygen out of the plastic. So that you underestimate the oxygen consumption because some of it's coming from the plastic. But then when you mix, suddenly you're putting into that well an oxygenated medium, and then you put the plunger down. And the plastic now sucks oxygen back out of that well. to replace the oxygen it lost earlier on during this hypoxic incident. So it's already sucking oxygen out, and by the time you get to take the first measurement, quite a lot of the oxygen is gone. So the well is becoming hypoxic, the plastic of the well is becoming hypoxic. And that means that you run out of oxygen even sooner than you did before, which is why when you have these rates, which are not too bad with ADP, they get worse with FCCP. It's because you've accumulated an oxygen debt here, and it's really showing up here, and it really screws up the trace. So whenever in a seahorse you see these very nonlinear rates, the gut knee-jerk response is to go look at the oxygen levels, see if you're running out of oxygen, see if you're mixing properly to re-oxygenate. And if you're not, that's the explanation for these rates. And if you don't know that, you'll say, wow, there's this really high rate with uncoupler here. But it's not, it's really high rate with plastic. The plastic seahorse well is a very fast respiring mitochondrion under those conditions of hypoxia followed by reoxygenation. So two things go wrong. One is you start at a low oxygen anyway, and the second one is you run out of oxygen, and therefore the rate of course drops to zero. And particularly if you were in the averaged rate, what you would see from this is some really odd bell-shaped curve of the response to the uncoupler, but it's using the machine wrong, not a biological response at all. So it's one of the main ways to use the seahorse wrongly is to not take this into account and not to cross-check by looking at the oxygen tension, whether or not it's behaving as you want it to. That's the main reason that seahorse recommend a particular range of respiration rates. They say, try and keep it always under about 100, 150. And it's because of this depletion of oxygen. So that's one way is to follow the recipe, but a better way is to see whether or not you've got a problem. You can see these rates are much higher than the recommended rates that seahorse says. So that's those uncoupled rates, and then we add antimycin and the rate drops to zero or close to zero. So you're happy with that. We've just poisoned the electron transport chain. No oxygen can be consumed because no electrons get through, except for the leak of electrons we talked about before, which is slightly less apparent here than the one that I was trumpeting. So maybe it was noise and not a real effect at all. And nothing interesting happens in the pH. Okay, so that's the two experiments. That's the system. What we're going to show you is the control experiments for the electron flow and for the coupling. And we're going to throw in some unknown. We know what it is, but you don't. And what we want you to do is to go off to the breakout rooms with the groups that you were in the prior break to talk amongst yourselves and try and work out what you think might be going on. And what we don't want you to do is to say it must be rotenone that you've added to cause this effect. What we want you to say is it must be an inhibitor of the electron transport chain that works somewhere between the substrate and the Q pool, because that's consistent with all of the evidence that you're presenting, or whatever it is that you think the unknown might be. So I hope you have, or at least one of the people in the breakout room has the unknowns. So you can carry this slide with you into the breakout room. So this is your first challenge. Here's unknown one. So the brown is always the control. An unknown one you can see is changing one of these respiration rates and changing in the electron flow experiment and changing some of these respiration rates in the coupling experiment. And what I want you to do is to try and work out what sort of effect unknown one must be having in this system in order to cause that. Unknown one is added in the well, otherwise it's exactly the same as the experiment we've just been through. So you know the reasons for all of these rate changes in the brown one, and therefore the lack of those rate changes should tell you what the unknown is doing in the two experiments. So we'll send you into the break rooms. We'll have a timer running for 5 minutes. And in 5 minutes time, we'll pull you all back here to the main room, and I'll get one of the breakout rooms to present their conclusion, and we can all discuss that and see if we agree that that's a good interpretation of the data. So Ricky, can you send it?
You're on the spot.
Okay. We thought that unknown one would most likely be an inhibitor of complex 2 because after the addition of succinate, we're still not seeing an increase in the oxygen consumption rate indicating that even with the presence of succinate, you're not able to get the electrons from succinate to enter the electron transport chain. And it was suggested that it could be malonate, but anyways, we were meant to just give the general sensor an inhibitor complex 2.
Does that explain both the electron flow experiment and the coupling experiment?
Oh no, sorry. Oh, oops. Oh, it is the same unknown in each
It's
case.
the same unknown in the two different nodes.
Okay, we misunderstood. I think we thought that like we were doing 2 separate things.
Okay. But the answer to my question is yes. So remember, in the coupling experiment, succinate is the substrate. And what you see in the coupling experiment is it's just flat lines. So it's the same as in the electron flow experiment, that once succinate is the substrate, it drops very strongly in rate. The logic that leads you to that, how do you know it's at complex 2 and not somewhere else? How do you know it's not at complex 1 or at complex 3 or 4?
In electron flow, we could see that prior to the addition of rhodonone, we can get electron flow. After addition of rhodonone, that goes down, which means that we're no longer fueling ubiquinol to continue going through.
That's right.
There can't be complex 3 because the asorbate and the TMPD are still able to have an effect.
Complex 4, yes.
Complex 4, yeah. But yeah.
Oh, yeah.
So these
And antimycin A.
So complex 4 is clearly fine. Complex 1 is fine. Succinate dehydrogenase is on a branch, so when you inhibit it, it doesn't affect the flow of complex 1 to 3 to 4. Whereas if you'd inhibited complex 3, you wouldn't have been able to oxidize the NADH linked substrates either, because it has to go through complex 3. Whereas it doesn't have to go through complex 2. So it's because of the branch that you can infer it's something to do with succinate oxidation. And then in this one, succinate's added, you just can't oxidize it because it's inhibited. Is there anything else it could be that would cause this pattern other than a complex 2 inhibitor? So think about the system. You add succinate to isolated mitochondria, what has to happen?
It has to be transported into the mitochondria?
Yeah. So do you think a substrate transport inhibitor could cause this phenotype?
Yeah, that would make sense as well. If you just can't get succinate into the mitochondria, that would potentially have the same impact.
Yeah. And how could you differentiate those two possibilities? Succinate transport inhibitor from a complex 2 inhibitor. You'd have to do another experiment. There's not enough information in the experiment on the screen.
The freeze and thaw or some sort of membrane permeability.
That sounds like Eddie. Eddie, this is what you do for a living. Yeah, so if you break the membrane, the electron flow is fine, right? It doesn't need any protomotive force, so the fact that breaking the membrane would disrupt the protomotive force is irrelevant. You've already got an uncoupler there. But it would allow the succinate now to get in. So if you added a bit of detergent and it still did this, it's probably an inhibitor somewhere in the complex 2 or beyond. It has to be in complex 2. It's not in the Q pool because that would affect the NADH oxidation. Whereas if freezing and thawing or adding detergent didn't, sorry, I'm not sure I said it the right round, but if freezing thawing helps, then it's a transport problem. If it doesn't help, it's a SDH problem. Yeah, so in fact, it was, you're quite right, it was malonate that we had there. So it's a competitive inhibitor, which probably explains why it didn't drop to 0 here. Arguably it dropped to 0 here, so it's not so clear why they're different. Again, they may not be exactly matched experiments. Malonate competes with the succinate for binding to complex 2. It also actually is a transport inhibitor because it competes with succinate for the carrier that lets the succinate in. So it's a double whammy as an inhibitor. And we like it as an inhibitor because it's competitive. So it's easy to wash off and you can get half inhibition if you wanted, or 3/4 inhibition, just by varying the succinate to malonate ratio. So it's a very friendly and helpful inhibitor. You can't use it in cells because it doesn't get in and succinate doesn't get in. But you may come across people using esterified versions of the malonate as they do with the succinate to get it into cells. So the dimethyl ester, you're masking those carboxyl groups so you don't have the polarity that stops it crossing bilayers. And then when it gets into the cell, various endogenous esterases chop off those methyl groups and release the malonate. So you can inhibit malonate, you can use malonate to inhibit SDH in intact cells as long as you present it to the cells as the methyl ester. Okay, good. So you get the idea, right? 5 minutes about the right length of time. Too short? Too long?
Maybe a tad bit more.
Okay, so we're playing off, running out of time. Let's make it just a little bit more because you kind of have the idea now what you're supposed to do. Let's try 6 minutes this time and see how we go. So the next one, they're out of numerical sequence just because it makes more logical sequence to go through them this way. So here's unknown 3. Again, it's doing something to the electron flow experiment. It's doing something to the coupling experiment. So let's go to the breakout rooms. I'll ask a different group next time to present what they think is going on with unknown 3.
You'll see your breakout room number when you're assigned to it. So just look at your screen when it.
I keep volunteering you.
So we see respiration with ascorbate and TPND, which means that complex 4 is still intact. And we don't see respiration with anything else, which means transfer of electrons to anything aside from, I guess ascorbate goes directly to cytochrome C, right?
Yeah.
And so anything before that could, I mean, it has to be, you know, between cytochrome C and the transfer point of electron for succinate, so, or NADH. So basically it's probably complex 3 or the ubiquinone pool that is not able to transfer electrons to cytochrome C.
And what about the coupling experiment? Is that consistent?
Yeah, I mean, if you can't transfer electrons to cytochrome C, then you're not going to get any respiration under any of those conditions that I can tell.
Yeah. So this one's completely dead. So clearly electron transport from succinate doesn't run, and that's confirmed in this one. Electron transport from succinate doesn't run. It doesn't run on the other branch from NADH either. So you've managed to do something that stopped both NADH oxidation and succinate oxidation, but doesn't stop ascorbate TMPD oxidation. So cytochrome C is probably intact because the ascorbate TMPD can push electrons in through it. So it's somewhere upstream of complex 4, and it's, in the simplest version, it's something common to the other 2 branches. And the only thing common to the other 2 branches is the Q pool and complex 3. So what your guess was what? That it was, I forget. The complex 3 inhibitor, was that your proposal?
We talked about that, and we were warned from being too specific about the nature of whether or not it's even an inhibitor. So I'm just going to say electron transfers impaired between coenzyme Q and cytochrome C.
Yes.
Probably complex 3 inhibitor.
Yes. So a complex 3 inhibitor would certainly do that. It would stop everything from succinate, everything from NADH, but it wouldn't stop from ascorbate TMPD. And then you rightly say that there are other things that might be going on. So if we had a magical Hoover, which could, is Hoover an American word? Electrolyte? Vacuum cleaner, which was able to remove all the Q from the membrane, it would also look like this. Or if we had some reagent that could bind to Q and just stop it working, it would look like this. And then I guess in the limit, if we had some multifunctional inhibitor that inhibited both complex 1 and complex 2, it would look like this. So there are some other options other than complex 3, but complex 3 is the simplest and most likely explanation for these data. So what it really was a complex 3 inhibitor. So this was antimycin A, fully blocks the electron flow through complex 3, or nearly fully, as I explained. So everything that feeds upstream of that can't be oxidized. Anything that feeds in electrons downstream of that can be oxidized. So ascorbic TMPD is fine. And in the coupling experiment, because we're running it from succinate, it can't be oxidized in the presence of a complex 3 inhibitor. So it was a complex 3 inhibitor. It might have been a Q antagonist or something more complicated. But the simplest interpretation is complex 3 inhibitor. Good, so getting the idea, right? So let's just address that question of, do you need more time for a known 5? Is 5? Okay, so clearly this one was a bit more troublesome because it's real data and it's doing a couple of odd things that make it a bit less straightforward. And that's going to happen more and more as we get into these more complicated examples. Group 1, you want to have a go at this one? What's that?
Group 1 is Nastia, Tyler, Ritesh, and Richard.
Yeah, we probably think it is the ATP synthase inhibitor for type 5, just because if we see the profiles, it looks almost following the normal trend, like on addition of retinone, everything is like it is having the effect. So like it's due to the presence of uncoupler, everything is going okay because it's nothing to do with ATP synthase right now. But if you see the coupling experiment, in that even addition of ADP does not have any effect, which hints us that it's probably complex 5 or ATP synthase is not working well or has some problem. So even addition of like further, due to that reason, we think that it's ATP synthase inhibitor which is probably present in the reaction.
So 2 things to pick up on. One is, could it be anything else other than the ATP synthase? And the other one would be, what about this funny stuff that's going on here and here and here? These are not things you would expect with an ATP synthesis inhibitor. So the first one, could it be anything else? Then, but maybe I need to do them in the other order. So what about these things here? Why would an ATP synthase inhibitor have these effects on the coupling and maybe this effect on the electron transport chain?
There's some ROS production going on. I don't know.
Yeah, something a bit less specific than that. So it could be some nasty side effect, which we're not very clear what it is. In this one, they're uncoupled before you start, so it's not all that likely it's ROS, because you wouldn't expect inhibiting the ATP synthase in an uncoupled mitochondrion to do anything to ROS. So this is an example of one which behaves like real biology. It's doing sort of odd bits and pieces that we don't really understand. Certainly if it's an ATPase inhibitor, you wouldn't expect these results, and there doesn't seem to be any coherent other explanation. I mean, you could say this is a mild uncoupling, so a little bit of increase in this rate, but you stop the ADP response, and then this could be a little bit of mild uncoupling, and then you can't make anything of this because of the artifact that's going on. But mild uncoupling wouldn't necessarily inhibit complex 1 over other things. Although you remember I did say to you that complex 1 is particularly sensitive to sort of membrane perturbing effects. So I think actually these other effects could be interpreted as non-specific membrane perturbing effects, that complex 1 just isn't very happy, complex 2 and complex 3 and 4 don't care. And that's fairly typical for a whole bunch of things that interact with membranes. And those things often uncouple a little bit. So it's a bit like we just added, if it's a complex 1 inhibitor, we added one that uncouples and destabilizes the membrane a little bit. And then the other part of the experiment to that same group, so you came up specifically with an ATP synthase inhibitor, but could it be anything else that would cause that same phenotype by acting somewhere else within the system to give that same result. Again, same as before, remember the various things that have to go on in order to get that response to ADP, to get this increase in respiration rate in response to ADP.
If nobody else goes, I'm gonna guess an ANT inhibitor or.
Yeah, so generically the things going on are the ADP that you add has to go in across the membrane on the ANT, and the ATP that's made has to come back out again. Also the phosphate has to go in and come out as ATP. So if you were to inhibit the adenonucleotide carrier, you would also prevent the response to ADP. So carboxyattractylate or boncoric acid, well-known inhibitors of the adenonucleotide carrier, could have that response. Inhibitors of the phosphate carrier might also do it, although it's slightly more difficult because phosphate goes in on so many other carriers like the dicarboxylate carrier that usually some can squeeze in whatever you do. But in principle, phosphate transport would do it. And then there's other slightly weirder things, like if you had a reagent that mopped up all of the magnesium in the matrix. The ATP synthase needs magnesium, like most ATPases, ATP synthases, as a cofactor. So if you removed all the magnesium, it wouldn't work. So that's in a sense an inhibitor of the ATP synthase, but in another sense it's not. So there's a number of different sorts of things that might have worked. And as you will have worked out by now, we're not giving you complicated things mostly. So this was indeed an ATP synthase inhibitor, so well done, group 1. Blocks the ATP synthase by blocking the FO part of the channel, the proton channel. And in principle, it does nothing in the uncoupled experiment. So this is, as I say, some membrane destabilizing effect or just a non-repeatable artifact or something. And same with these other effects. So it's a bit like real world where you can see the signal that is the true signal once you know the answer, which is you've stopped ATP synthesis, but you also get these other peripheral signals that aren't necessarily quite as easy to interpret. And this is an example of that. We didn't expect those things to happen, but they did happen. So now we have to try and interpret them and see what we can do. So a bit of membrane destabilization by just having too much oligomycin present, because obviously in this one there's already oligomycin added. So we're just adding a bit extra. It's not going from 0 to something, it's going from 1 unit to 2 units. Okay, so next one will be unknown 4. So this looks nice and clean, so this might not take quite so long. Shall we do 5 minutes or the same thing? Come back when you're ready. At 5 minutes, we'll bring you all back in, because this one shouldn't be so difficult for you to work out what's going on.
That oligomycin experiment, I'm still very confused by why it would have higher basal respiration.
From the data, I think it's hard to explain it other than a bit of uncoupling. So in the coupling experiment, you see these increases. You don't see increases in the uncoupled rates. So that's all consistent with just a bit of uncoupling, either because it was genuinely uncoupling, or maybe even we managed to get some uncoupler into our stock of oligomycin in that experiment or something. Because it's not known as an uncoupler, oligomycin, so it's not a normal result. And the slight inhibition of complex 1 that you saw in the electron transport experiment, again, would be consistent with that. As I said, complex 1 is really quite sensitive to membrane perturbation, so it's quite easy to decrease its activity for reasons that aren't really understood, maybe to do with the active-inactive interconversions, or maybe it's just easily oxidizable or glutathione or one of these other modifications when you stress the thing a bit. It's not a very satisfactory interpretation, but it's an example of real data, which is why we left it in and didn't edit it out, because you have to try and see a signal under the noise sometimes to work out what's going on for the main game, and kind of ignore the minor things. And then other times the minor things are really telling, and it's hard to make that balance between those two things. It helps if you've done it 3 or 4 times though, with a class and gone through it. Then it gets really easy and you can't understand why other people can't see it.
Last example, you saw lower respiration with FCCP, and that's been reported a lot for oligomycin and the Ouroboros as well. Do you know why that happens?
I have an idea.
With the complex one.
Yes.
The others were more or less okay. Somebody had an idea? Do you want to-
But mine was really related to cells. I don't know if this would apply to isolated mitochondria.
Well, share.
Which is that after you've inhibited ATP synthesis with oligomycin in a cell, if glycolysis can't keep up with the ATP demand, the cells just go into energetic collapse. And so then you'll never provoke the maximal respiration that the cell could do if it had a better ATP-ATP ratio going into the uncoupling.
So that works well in cells. It really doesn't work as an explanation in the mitochondria.
Yeah.
So I don't think we really do know what's going on. My best hypothesis is that we're just overloading this system with a lipid-soluble large molecule, and it's just making the membrane a bit unhappy. And complex 1 is really rather sensitive to that, whereas the other complexes don't care very much about that. So it's often the case that non-specific things will be mild inhibitors of complex 1. So I would say it fits that pattern, and that would agree with this, where it looks like a bit of uncoupling is going on as well, which oligomycin should not normally do, but seems to have done in this case. Maybe we had a bit of contamination in there, or maybe we added too much or something.
We think it's inhibits complex 1. So the only readings where there's a difference between the control is right there, where you provide substrates to complex 1 with pyruvate and malate. And it's consistent with a complex 1 inhibitor, like, for example, rotenone. But when you provide electrons to complex 2 with succinate or complex 4 with ascorbate, then you see normal respiration.
Yeah, so clearly everything's okay beyond succinate, both in the coupling experiments, there was no effects on the coupling, and in the electron flow experiment. So you block the ability of these mitochondria to oxidize the added pyruvate and malate and use them to reduce the Q pool, but they can reduce the Q pool from succinate perfectly well. So it's somewhere between the addition of pyruvate and malate and before the Q pool. And what's in that compartment? One of them is complex 1, but what else is in that group of things?
I'm not sure on that one.
So remember, we went through it earlier on. So pyruvate has to go into the mitochondria, go through pyruvate dehydrogenase. You need CoA in the matrix to provide the CoA to make the acetyl-CoA. The malate has to go in on the dicarboxylate carrier. Malate dehydrogenase needs to work in order to reduce the NADH. So if you added a PDH inhibitor, maybe you would see exactly this. So the inference that it's a complex 1 inhibitor is perfectly reasonable, but there's also other things that would do this, such as a pyruvate dehydrogenase inhibitor or a malate transport inhibitor, for example, would do this. Although it's quite hard to stop malate going in without stopping succinate going in, so knowing other things can reduce the probabilities of some of these other possibilities. Yeah.
If it was only inhibiting one of, like, for example, malate dehydrogenase or pyruvate dehydrogenase, wouldn't you still expect to see a little bit of oxygen consumption at first until it had to build up? Yeah.
You would, although in this case, remember, they're in the well, so they've had a chance to do that before you actually get it in the machine to measure. So it might be that it did go for a bit and then stop by the time you get it started in the experiment. You have to test that by adding in flight before you could say whether there's something going on. So yes, it was a complex 1 inhibitor, rotenone, exactly as you described, just stops complex 1 from working, doesn't stop anything else, so everything else is just fine. Good. Okay, unknown 6, lots of weird things going on here. So not doing very much in the electron flow experiment, completely screwing up the coupling experiment in some way. Into your breakout rooms, again, 5 minutes should be enough.
So the CRS also has a pH probe, right? And in the morning we were mentioning the proton motive force. Usually the pH, delta pH part of the formula is not actually used because there is no way to measure it, or people usually do not measure it. Can we not use the pH probe to measure the pH?
Not in the trapped volume of a seahorse. So clearly you can use a pH probe to measure the pH, but what the seahorse allows you to do is to do it in the same well in parallel, which is just mechanically difficult. So it's handy that you have the probe in the well at the same time. It's interesting, even though I told you always to look at it, we're not using it very much in these explanations. So I'm maybe telling you to do something and then not doing it myself.
E-car trace?
Sorry?
E-car trace?
Yes, we're not using them in these explanations, are
Oh,
we?
they're not in the explanations.
Yes. Kind of wild and woolly, this one, right? Who haven't we had yet? Group 4?
That would be us. We believe this one is an uncoupler, similar to FCCP, because in the electron flow, you already have FCCP in the initial medium and the two tracers look nearly identical. Whereas in the coupling flow tracers, you see pretty massive differences. And the interesting peaks show the increase in oxygen consumption rates more quickly depletes the oxygen within the microchamber, and that's why you see the depletion of signal as it goes.
Yeah, exactly. So the inference here is that for the electron flow experiment, which is already uncoupled, nothing happens. So it's not doing anything to the electron transport chain because this probes all the different parts of the electron transport chain. So it's doing something in the phosphorylation system or the coupling experiment only. And then all this weird and wonderful stuff we kind of understand from what we've been through before. This is the rates are just too fast and it's running out of oxygen. So you're getting these over fast rates that drop off in time. And that's just a symptom of the rates too big. But what you can say is that when you poison the electron transport chain with antimycin, you do stop the rate. So it's still mitochondrial electron transport. It's not like we added in glucose oxidase and glucose or something, and the whole system is just consuming oxygen, because we can still take it out with the mitochondrial electron transport inhibitor. So it's the electron transport chain going too fast. There are not many ways to achieve that. The easiest way is just to uncouple. So the simplest interpretation is this is a whole bunch of uncoupling. Which is what it was, FCCP. So exactly right. We get this very high rate, which there's an explanation for here, which is perhaps in the interest of time, we won't bother to go through. It's just a little tweak on the experiment. So that goes through the artifacts that we've already been through before. Okay, good. 2 more to go. So let's to run these. So unknown 7, this is doing something in both traces. 5 minutes and then back, and then we'll do the last one. And so about 15 minutes till we finish. If anyone wants to leave, I apologize for overrunning. So feel free to leave unless you think there's still something to get out of the course by doing the remainder. So 5 minutes in the breakout room. More interesting as we get near to the last couple. So this one's a bit odd. Group 6. What's your view of this one?
Okay. Anybody wants to go? Group 6.
Looks like you're volunteer.
Yeah. So we think it's a complex 4 inhibitor because after complex 4 inhibition, we also think there is some kind of ROS buildup here. So that's why we are seeing a small change here on after succinate. And we were kind of not sure how to explain the coupling, but yeah.
So you're explaining this by a complex 4 inhibition, this by a leak of electrons to ROS.
Yeah.
And this one you're not quite sure how to explain.
Yep.
So I think you're part of the way there. So I mean, if you just stand back and look at the data, what you can say is that every rate has been decreased. reflect these basal rates, which maybe were just in the noise. So whenever there's a rate, whenever you try and go fast, you can't do it. So I think the fact that the ascorbate TMPD oxidation is one of the ones inhibited tells you that you've done something at the bottom end of the chain, cytochrome C, cytochrome oxidase. So I don't think you need any Ross explanations to explain the rest. If you assert that this is a complex 4 inhibitor, that would explain why you can't oxidize succinate very well, why you can't oxidize pyruvate and malate very well, and why you can't oxidize succinate very well when you add ADP or you add uncoupler. So a complex 4 inhibitor is an adequate explanation. It's just not a very good one, right? Because there's still a bit of a rate left. Again, the usual question, what else could it be? So it might well be that, but what else could also do this? And how about an antibody to cytochrome C? Do you think we get this result with that?
Yeah.
Yeah, maybe. I mean, if the antibody could get at the cytochrome C through the outer membrane, so you have to say the outer membrane was a bit messed up by being stuck down in the seahorse plate. But for all of these, you also need cytochrome C to be working. So if somehow we decrease the ability of cytochrome C to work with some sort of antagonist, we would also get this result. Of course, it is a complex 4 inhibitor, so we used azide. I think we used it at 20 millimolar, which we thought was plenty, but it isn't enough. So clearly, we've only partially inhibited the electron transport chain, and it does have a residual activity. So we underestimated the amount we needed to completely poison the hemes, but we were able to decrease the respiration rate across the board. Good. One more to go. We've kept the real Lulu to the last. So unknown 2, this is behaving bizarrely. Let's see what you make of it. We'll come back in 5 minutes. For this one, I would come back anyway, even if you don't understand it, because it's kind of weird. And the explanation is interesting, but to get to the explanation is relatively difficult from the data. So, group 7, do you want to have a go? And if you don't get it, that's fine, but have a go. Does group 7 know who they are?
Do you want to go or do you want me to go?
You can go.
So it was a shot in the dark for us because it inhibits complex 1 activity, but enhances complex 2 activity, and then looks like an uncoupler.
Yep.
We said succinate. Why not?
So, I mean, the final step is a shot in the dark. The diagnosis looks to me pretty good. So it's clear if you look at the coupling experiment that it's like an uncoupler, right? So this behaves the same as the excess FCCP behaves, and it's inhibitable by antimycin, so it's still regular electron transport that you're looking at. So it's uncoupled electron transport in this one. In this one, you've squashed complex 1 completely, and then you've kind of had a couple of weird effects on succinate oxidation and the slight inhibition of the ascorbate oxidation, but at least at the first pass, they're still running. So this one, we thought we were being really clever. So I'll backtrack to the story and then come to the solution. So when you permeabilize a cell in the seahorse, you can directly access the mitochondria and you can do these experiments in permeabilized cells. But one of the things you have to be really careful with is the calcium. So you grow cells in 2 millimolar calcium, but if you present more than 1 micromolar calcium to isolated mitochondria, they take it up and explode. Literally, they swell up and they burst. So what we did was we put 2 millimolar calcium into the mitochondria, knowing that they would just die, nothing would happen. And then to our surprise, we saw this. So the interpretation here is that actually they don't just die, but what they do is they do explode. So you give these mitochondria calcium and they take it up because it's driven in the coupling experiment, and that fully uncouples them. So you blow up the membrane so they're permeable to everything, including protons. So it's like adding an uncoupler, but they're still respiring, so you can inhibit with antimycin. The surprise was that blowing them up stops complex 1 activity, but doesn't stop the rest. And then we realized that there's a definite difference with complex 1 activity, and that is it accesses a soluble NAD pool in the matrix. So the pyruvate and malate go in, and then you need NAD and to make NADH, and then complex 1 needs NADH as a substrate. And once your mitochondria have exploded, the NAD pool is diluted out into the medium. So there's essentially no NAD around. So you can't run complex 1 because you can't get any NAD reduced, or if you get it reduced, it can't then find the complex 1 to act as a substrate. And the surprise to us was that, but succinate oxidation is just fine. What we expected to happen was when you blow up the mitochondria, the cytochrome C comes off the membrane, and therefore you can't run complex 2 and you can't run ascorbate TMPD oxidation. So we expected they'd just be dead. But we realized after we saw the experiment that that view is based on a classic ionic medium. And in a classic ionic medium, the cytochrome C falls off the membrane. And calcium does indeed completely inhibit respiration, which, if you're still remembering from my lecture, is Johnson-Williams state 5, I think it is, or state 6, whichever it was, where you completely inhibit everything by using excess calcium. But these experiments are done in a sugar-based medium. This MAS is a mannitol sucrose-based medium. And in that non-ionic medium, the cytochrome C sticks tight to the membrane, even when you blow the membrane apart. So the calcium goes in osmotically, everything rushes in, the mitochondria swell, they burst, but the cytochrome C stays tight on the membrane. So what you have is membrane fragments, and you give them succinate. Some of those fragments have got SDH on them, so they work perfectly well. They've got Q in them, they've got cytochrome C stuck to them, they've got complex 4 in them, so they oxidize succinate, completely uncoupled, but they oxidize succinate. And the same with the ascorbate. The ascorbate can feed that cytochrome C that's stuck to the membrane, and you would get ascorbate TMPD oxidation. So the answer is we added a lot of calcium, they take it in, that blows them up, and that causes them to become uncoupled because there's no intact membrane to maintain a protomotor force. NADH oxidation is completely destroyed because the NAD is diluted away into the medium. But solid state biochemistry allows complex 2 and complex 3 and complex 4 to run, so you still see uncoupled oxidation of succinate and ascorbate TMPD. So for us, that was a learning experience. We'd expected one thing, we saw something else, and eventually we were able to rationalize why we got that result. And so it's a good example of you can, from the data, come to that conclusion, although it's a long and tortuous path. But even when you think you know what's going on in the seahorse, sometimes you do experiments and you get results you just don't expect. And this was an example of that. And only in retrospect should we have expected it. But the underlying lesson still remains true, and that is that if you take a cell in the seahorse and you permeabilize it, the mitochondria will all die. They'll become completely uncoupled and they'll stop oxidizing NAD substrates. So when you permeabilize cells, you have to simultaneously lower the calcium to 1 micromolar or less. The easiest way to do that is to add EGTA along with your permeabilizing reagent so that the calcium instantaneously drops to below the point where it causes this phenomenon. So be very careful when you permeabilize cells that you do it in a medium that's equivalent to the mitochondrial medium, to the cytosolic concentrations of calcium in particular, because mitochondria will avidly accumulate any calcium they see. And that's one of the reasons why in a cell experiment, if you break a cell, it doesn't matter so much, as you might expect, for the respiration, because as soon as you break it, the NAD all comes out and the mitochondria in that cell don't respire. So that it becomes invisible very quickly to the oxygen measurement. So the seahorse is relatively impervious to killing of cells because those cells just drop out and don't do anything. It's quite hard to catch the uncoupled period in the cell because they need NADH to oxidize, and you don't see this, which is succinate driven. There's usually no succinate around either because it's also dissolved, diluted out. Okay, so a marathon day. Your brains, I hope, are throbbing. If they're not, you haven't been paying attention. The conclusions from the mitochondrial respiration are that you can do it really easily in this plate-based format, but there are bits and pieces you need to watch out for, particularly respiring too fast. You've got lots of control over the experiment, but that's a two-edged sword. You also have responsibility for the additions that you make, and sometimes you make additions that don't make sense. And also pairing together the electron flow and the coupling experiments is actually a very quick way to quickly find out many things about what your reagent or your treatment does. So it's a good first place to start, but you often would need to do more complicated experiments to pin down exactly what's going on. Okay, so ends day one. Thank you for staying with us. And tomorrow we start at 9 a.m. Pacific time with more lectures and more practical sessions, 2 of them tomorrow. So another entertaining day tomorrow. And thank you very much for being here. Any questions or comments before we close? Okay, then thank you very much, and we'll see you all tomorrow.
Thank you. Good night.